example on radioactivity. So let's see what they are. Yeah, the questions here. What I would advise is everybody try this for 2 minutes and then we'll see. Don't worry about the calculations. Try the concept here, like what you're going to do. So don't worry about calculations, and I'm going to show you what the solution is. Okay, so let's see what we are going to do here. So decay constant is given. So lambda is given to me. Kind of given. I'm not going to write that number there. So just given there, right? Now you got to find the activity. Activity kitna hai? Activity is initial activity. That's what they're saying. Lambda times of how many nuclei you start with. Lambda दिया है, n not पता कर लो, right? So a sample of 1 microgram, right? So try to do that way. Atomic weight भी दिया, सब कुछ दिया. It's so clear here. चलो, we'll do it together. ठीक है? तो 1 mole में क्या होता है? 1 mole is basically the Avogadro's number, right? Those number of molecules or the nuclei you have in 1 mole. So 1 mole is 63.5 grams has Avogadro's number of molecules. तो 1 ग्राम कितने कितने होंगे? 1 ग्राम में होंगे Avogadro's number divided by 63.5. But we are talking of 1 microgram. So 1 microgram में कितनी nucleus हो गई? Avogadro's number divided by 63.5 multiplied by 1 microgram. These are the number of nuclei that you have. And then you go ahead and multiply with lambda. That's all you do. You just use lambda times n naught. I'll show you the calculations here. You can just go through that. ठीक है, Avogadro's number आ गया. Avogadro's number divided by whatever is 1 mole and then times whatever is the mass that you have. That is the number of nuclei you start with. And you multiply that by the lambda that is given to you. It has to be given to you, right? Okay, any questions, any doubts, please tell me. I don't agree that nobody has any questions here. Okay, Atri, Rhythm, Ganit, okay, anybody. Oh, that's Curie actually. Sorry. I think that was not covered maybe. Okay, so ये जो activity है ना, activity was whatever we covered, becquerel. So 1 becquerel is 1 integration or 1 decay per second. ठीक है, that is 1 becquerel. Becquerel is the unit of activity. Activity is in this one, right? But that's too slow. So usually we use Curie. So 1 Curie. So let's write it like this. So 3.7 times 10 to the power 10 becquerel is 1 Curie. So radium का क्या होता है? Why this number? Radium. 1 gram of radium actually has 3.7 into 10 to the power 10 number of decay per second, and that is why we are using this number Curie. So CI stands for Curie, the Madam Curie, that same Curie, to honor her. So 1 radium का क्या होता है? 1 Curie is the activity there, and that is why what we have done is this is becquerel, and then you divide by this and you get number of Curie. Clear? And if not clear, I will explain again, please. Atri, clear? Atri, everybody. Okay, ठीक है. ठीक है, clear है तो that's good. Okay. Okay, Abhinaya says clear. Try this question again. The same thing. We'll just ignore the calculations out there. I want to start fusion and fission after this. Just go through the approach and then we'll do it together. Okay. Now this is very easy. You know the decay constant you can find from half-life. Decay constant is, or you start with the expression for half-life. Half-life is 0.693 divided by the decay constant. They're telling you the half-life. You got to convert that into seconds. You say 2.57 days times 24 hours times 3600. This is what you plug in here and you calculate lambda. The average life is 1 by lambda. And then you can do the same thing that we did for the previous question and find the activity. I'm just going to show you, and you can take a screenshot if you want. Right, you got to convert all that into seconds. It's given in days. You got to convert into seconds because that's more like SI unit. You can say decay constant is per second there instead of saying per day, which is does it's not an SI unit. Okay, is it everything clear or no? Yes or no? Because I'm not sure. Nobody is asking question. Is it clear or not clear? Is it confusing or is it clear? हाँ तो ठीक है, but I don't want to slow down the class. I want to keep the pace also, but just want to make sure that you're getting it. But then only half of the class is responding. So what is the other half of the class's opinion? Have you understood it or not understand? Because I only got 60% votes so far, or 67%. Okay, ठीक है. True means you understood. False means no, it's not clear. ठीक है. So 2/3 of the students have responded with positive there. ठीक है. If you've not understood, you're supposed to tell me at least in the anonymous poll there. So 1 by lambda and activity, we already did all that. 1 mole has Avogadro's number of atoms or the nucleus. We are interested in nucleus. So nucleus. Fission. अब fission पे जाएंगे, ठीक है? Radioactivity हो गया. Anybody has any questions is supposed to ask me. No more radioactivity slides after this. So we are talking of fission. So let's briefly see what is fission. Fission में क्या होगा? We'll take a big nucleus, a heavy nucleus, and break it into two smaller nuclei. ठीक है, break कर दिया इसको. In addition, you get some energy. अब ये energy कहाँ से आई? There was some mass here, right? Maybe, like, I'm just giving vague numbers here. 0.5 m, and this is 0.49 m. The rest of the mass is gone. It's not appearing somewhere. So that mass actually is converted into energy. So this is more like a brief kind of overview of what is happening. This is fission. अब fusion में क्या होगा? Let's see fusion also here. Fusion में we'll take two nuclei. So let's say this is M and this is M. This gives one big nucleus. Fuse कर दिया, fusion. Right, maybe this is 1.9 M plus energy. Okay, now why is there is a difference in mass? We will see that because of the binding energy. We will see that. But this is in nutshell what is fission and fusion. This is what we use. We use like nuclear energy. When we talk of nuclear energy, this is what we use. This is also, so we use for power generation. So when we say there is a nuclear power plant, we are talking of nuclear fission actually. Destructively, this is also nuclear bomb. Hiroshima, Nagasaki. This is nuclear bomb. Destructively. Okay. Now this is what sun uses. So Surya Devta, that's what he does. Sun takes two hydrogens, combines to make a helium and lot of energies. This is what sun does. Now destructively, this is atom bomb. Right. So this is what North Korea recently did a few months ago. It tried atom bomb, right? So this we don't have the technology to harness right now. This is more energy actually. More energy compared to the fission. Please also remember this. Nuclear fusion will have more energy compared to fission. Okay, but today we have technology to use fission. We use fission. Any questions? Any doubts? Anything in that summary? Clear है तो चलेंगे आगे. But you're supposed to ask questions if it is not clear. ठीक है? तो अब देखते हैं fission में क्या हो रहा है यहाँ पे. Uranium 235. So uranium comes in different isotopes 235, 236, 237, 238. But only 235 is useful for us. And this is what the world is fighting for. I don't know how, if you follow the news, there's a treaty signed between India and Russia maybe to get nuclear fuel. What we are talking about is to get uranium 235. Uranium 238 is useless for me. Uranium 236 is useless for me. It is uranium 235 that is going to be useful. So what happens here is this is uranium 235. ठीक है? It is unstable. तो एक ball है suppose. This is unstable and it wants to break apart. But it cannot break because it is at the verge of breaking, but it doesn't have energy to break. So it's kind of trying to break. So what you do is you take a neutron. This is a neutron here, and you collide with that. So इसमें already energy थी and it was unstable, right? It had so much of energy, it wanted to break, were not able to break. So you're now making the situation worse for it because now you're providing some energy. Neutron is coming with some kinetic energy which becomes part of this. So this becomes uranium 236 now, and which is excited. It has so much of energy, and that breaks into krypton and barium. Because now this can break. It has so much of energy that it breaks. So what happens now? It breaks into barium and krypton, but then three neutrons are also released. Now, when it says energy, we are talking of half mv square here. Neutrons are moving with a very high velocity, and this is the energy that we are talking about. So when you're talking of energy released, that's all the kinetic energy of the neutrons, which you can use. Right? You can use to heat up water. You have this in a pool of water, and I should have brought that image. Maybe I have a very nice image. I'll bring it next time maybe. ठीक है. So now these neutrons are going to collide with water molecules. Water molecules get the energy and start vibrating more. That means the temperature of water has increased. The water will become steam, and that steam can run the turbine. ठीक है. So there are two things that happened just now. What happened is there was a fast moving neutron which actually was used up to heat the water, but in the process this neutron will slow down. And why is that useful? Because only slow neutron, or I will say moderate speed neutrons can do that. So what we'll do is, this is a moderately speed now. You can use it. Actually, I will actually remove this. This is a kind of chain reaction now. क्योंकि अब क्या हुआ, we remember we needed neutron to make this happen. We have 3 neutrons. So now this neutron can make further uranium 235 break. This can make another break. This can make another break. So now you have 3 neutrons here, 3 neutrons here, 3 neutrons here. You started with 1 neutron, one reaction. Now you have 3 reactions. Next you will have 9 reactions, 27 reactions, 81 reactions. This is a chain reaction. Now if you leave it uncontrolled, the energy is so much that it is a bomb now. But if you control it and you say, okay, let me do this, I'm going to somehow absorb these, two of these, two of these, two of these, you're controlling. You're saying, okay, we're going to control any extra there. So if there are 1 lakh of these neutrons doing the fission here, again 3 lakhs are released, but then 2 lakhs I eat up, and then 1 lakh are doing. So this is a controlled, and this is a nuclear reactor. So controlled is a nuclear reactor, uncontrolled is a bomb. Any questions, any doubts? Okay, nobody is asking doubts. That is not convincing to me. Atri, Ganit, Abhinaya, M. Ashik, Manju Shiri, Ninad, Rhythm, Rukaya, Sai Kumar, Shivangi, Shreya Bhatt, Shreya Hegde, Trisha, and Vasudeva. Nobody has any questions? Are you sure? Are you really sure there is no question at all? ठीक है, ठीक है. If there is no question, that's fine. No worries. So I don't know. Nobody asked me this question. Why do we need moderate energy? Why do we need moderate energy there? Can anybody answer that? So this is what I'm saying. There is a neutron here, and this is uranium 235. It breaks into barium. I'll write it there, barium and krypton. But then you also get 3 neutrons here, and they're fast moving. And I'm saying these are useless. They cannot perform any more chain reaction unless you slow them down. So why am I saying we have to slow them down? Anybody who knows the answer, please type it on the chat box. Or if you want, I can unmute you. You can answer on the microphone. Anybody? Shivangi, Vasudeva, Shri, Sai Kumar, Abhinaya, anybody? Atri Patel, Rhythm, Ninad. Anybody can answer that? No? Yeah, but then this can also collide with another atom, no? You can collide with uranium 235. But I'm saying when it collides with U-35, it does not do anything. No, 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 no. Sai Kumar has given a valid point, but that is not the reason. So Sai says, if it is very fast, you cannot control it. I'm saying control is not even the point. Let's say this is a bomb that we are trying to make, which is not a good thing to talk about even. But let's say what I'm saying is this will not have a fission now. So if it is moving fast, it will not do the fission at all. That's what I'm trying to say. Useless in the sense it will not make the fission happen, even though it has more energy. So Ninad, the question is, if this is fast moving, this cannot make the fission happen. The reason is this. Please, everybody, focus here. What I'm trying to say here. Uh, no, 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 no. Abhinaya, yeah, nice try, but let's see. Let's see. I cannot write here now. One second. Okay. So don't try this, obviously, but this is what you might have seen, observed in movies or somewhere. Let's say there's a glass window. Never try this place. Okay. This is a glass window. If you take a stone, what happens? And throw that on the glass window, what happens to the window? If you take a stone. What does the stone do to the window, please? Everybody tell me. If you take a stone and throw it on the glass window, what does it do? It shatters, like Shivangi says, Sai Kumar says, it breaks the window. Right? It breaks the window, obviously, right? Shreya also says Shreya, but okay. Now let's take a bullet, like a gun, and fire on the window. What happens when the gun bullet hits the window? What happens now? Like from intuition, common sense, or seeing somewhere. Abhinaya says it does not break the window, it leaves a small hole there. So what happened just now? Yes, yes, yes. Right? So like Sai Kumar is also saying, and Shreya is also saying maybe it cracks it a little, but it doesn't not break it. Why? Because the gun bullet was going with such a fast velocity, it did not have enough time to spread its energy around. Stone was so small that it spreads its energy there. So even though gun bullet had more energy, but it was so fast that zoom, the window doesn't even realize what happened. Okay, now Abhinaya says, I get it. Now exactly this is what is going to happen. Let's say this is uranium 235, and then you have a very fast moving neutron just goes through that. Nothing happens. Now, if it is moderate speed, what happens? It comes here, becomes part of the family here, and this is where there is so much of energy because it is staying there. It was unstable. Another neutron comes in. Oh, we have more of that. So now it breaks. So you need a moderate energy level. Okay. So this is why you need a slow moving neutron. Now, these things I'm not just telling for information, these things can also come as exam questions. Okay, chalo, aage we'll move on. So each atom that undergoes fission, you get this much of energy. So how much of the mass has to go decay? How much mass you need every second, every hour to get this much of power? Take your time, no rush. Anybody, please. Now, obviously, the calculation is too much, so let's do it together. Okay. Now, what you need is you need this much of megawatts, right? So one of the atom provides you this much. One atom. Ek atom will give you this much. Now you need 300 or 3000 megawatts. So these many joules per second. Does everybody agree? This is these many joules per second. Now one atom can provide 200 times 10 to the power 6 times 1.6 times 10 to the power minus 19 joules. These many this is the number of atoms, or like this is the amount of energy one atom can provide. So this is the total number of atoms that you need every second. ठीक है, this is every second you need these many. अब एक एटम का कितना मास है? One atom is equal to 235 atomic mass units, right? You convert it into kilograms and then you multiply that with this one number, and that's how you get the number of, or the mass of one in 1 second, how much mass has to disintegrate. Or in 1 hour you can multiply by 3600, or in one day you can multiply by 24, right? So I'll show you the calculations here. This is what you need to do. Any doubts, any questions, please ask. Do not hesitate, please.